we'll take a look at how many significant figures are allowed as answer. It's mixed. The two rules that we have to deal with. We have to deal with multiplication and subtraction. So when we're dealing with addition and subtraction, I'd like to line up the decimal point here and then see how many decimal places we're allowed. So addition and subtraction, we're allowed 2 decimal places here. And so if I subtract these two, I'm going to get 0.07. That would be 2 decimal places. And then I'll do the multiplication. So the next step would be 0.07 times 10. And that would be 0.7. And so here, 2 decimal places ends up giving us only 1 sig fig. And therefore, I'm only allowed 1 sig fig here. And so for addition and subtraction, we use the fewest number of decimal places. For multiplication and division, we use the fewest number of sig figs. So it's a little bit of a trick question. Yeah, so I did it separately here. So first I did the subtraction and then figured out. And then I look, how many sig figs do I have left here? It's just 1.
What if you have like a big stoichiometry problem and maybe it's like a compound where there's also addition subtraction, and you plug it into your calculator, but like in one of the steps it comes out is less sig figs. Because when I see this, I look at numbers there. I don't look at the intermediate calculation numbers.
Yeah, like you say 3 sig figs, so we're allowed 3 sig figs in the final answer. Yeah. If this addition and subtraction, then you have to, it makes it a bit of a pain because you have to do that separately. So you can't combine that into one calculation and look at the fewest number of sig figs. So in this case, it turned out to be 1. So we have to do it in steps. We can't combine it. So you have to make sure that they're consistent with the one set of rules. Before moving on to the next set of rules. Is that okay for that one? Okay, you had other ones? Number 8. A carbon-12 atom. This one is a mistake on the key. I made a mistake on the key. I put down B, but that's not correct. What's the correct answer? A. So if you put down A, then I'll credit you for that.
Put down B.
If you put down B, did you?
Yeah.
I won't deduct. We put down B. So you'll get the 2 extra points if you put down A. Yeah, if you have an A, I can do that. Okay, next one. Number 12. A mole of protons weighs about 1 gram. What did you put for this one? True or false? You put false. Do you know how much 1 proton weighs about? So this one involved a bit of memorization because you'd have to know that 1 proton weighs about how many U? Yeah. And so this is about 1 U per proton. But because of the way Avogadro's number is defined, the mole and Avogadro's number and the U are defined, then it's numerically the same. 1 U per proton is numerically going to be 1 gram per mole of protons because of the way we define it. So it's like a hydrogen atom. A single hydrogen atom weighs about how many U? 1 U, and a mole of hydrogen atoms is going to weigh about 1 gram. And so a proton is pretty much a hydrogen atom minus an electron.
So that's true.
Yeah, this is true. If I said a mole of hydrogen atoms weighs about 1 gram, would that be true or false? It would be true. So hydrogen's mostly H1. There's a little bit of H2 deuterium, minus the electron. So it's true. And there's a numerical relationship as well. Sometimes we use proton and hydrogen interchangeably, but usually when they're talking about it, they're talking about the hydrogen ion. And so when we talk about proton transfer in acid-base reactions, we're talking about hydrogen atoms transfer. And so that's for number 12. Okay, did you have more on that? 29.
So if the question said that if a mole of hydrogen protons weigh about 1 gram, that would be true as well, or okay.
Yeah, a mole of hydrogen atoms weighs about 1 gram. That's true. Hydrogen atoms are made up of pretty much most of the hydrogen atoms found in nature are made up of 1 proton and 1 electron. The electron doesn't weigh so much. And so oftentimes the electron's mass is ignored. The electron weighs 1,850 times less than a proton. It's about 2,000 times lighter. Twenty 29, you have to know a few other things, like chlorine-35. A chlorine-35 is going to weigh about how much? 1 chlorine-35. Well, a chlorine-35 consists of 35 protons and neutrons combined. And so each proton and neutron weighs about 1 U. And so if we have 35 protons and neutrons, we call them nuclids because they could be a proton or they could be a neutron. If we have 35 nuclids and each nuclid weighs about 1 U, then a chlorine-35 is going to weigh about how many U? 35 U. And so this is going to weigh roughly 35 U. And then we have a chlorine-37. Natural abundance of chlorine-35. Oops, I forgot to give you chlorine-37, didn't I?
3 points.
I might have accidentally deleted it. Sorry. Yeah, I think I accidentally deleted it. I was supposed to give you chlorine-37. So number 29, it was not a fair question. So what I'm going to do is I'm just going to give everybody 2 points, which I think, unless you already got 2 points. To keep it fair, I think. I'm not sure. Oh, wait a minute. This means that 100 grams of chlorine. No, this you don't need it. I'm not asking you to do any calculations. This problem is asking if the percent is a mass percent or number / mole percent. You should know in the mass spectrometer, is it a mass percent or a mole percent? And so in the mass spectrometer, you have a detector. And the detector is going to generate a peak depending on how many atoms strike it. The more atoms that strike this, the bigger the peak will be. And the fewer atoms that strike it, the smaller the peak will be. Here. And so it's based on how many, not how much they weigh. How much they weigh will be, more forceful collisions. No. And so now that I look at this problem, natural abundance of chlorine-35 is 75.77%. Is that a mass percent or mole / number percent? It's a mole / number percent. These are not mass percent. And so what that means is that if I'm making this a mass percent, 100 grams of chlorine, there's 75.77 grams of chlorine 35, that's wrong. That's wrong because of the way the mass spectrometer works. And so you have to know that how the mass spectrometer works. So sorry, I thought this was a calculation for the average atomic mass of chlorine. And so this is false. What that means is out of 100 atoms of chlorine, 75.77 will be chlorine. So if I have 100, about 75 will hit here and 25 will hit there. That's what that means. Or, you know, there are only 2 isotopes here. So 75 out of 100 hit here. Does that make sense? The correct answer would be false. Oh, the true answer? Okay. Means that in 100 atoms of chlorine, there will be 75.77 chlorine 35 atoms. And so the way I read this is you can't have like a fraction of an atom. You have to have whole atoms. And so what I do is I move the decimal point to get rid of that. And so you'll have 75.77 chlorine 35 atoms out of 100 chlorine atoms. And so to get rid of the fraction of an atom, I'll move the decimal 2 over. And so the same thing here, I'll move it 2 over. And so if I move it 2 over, that means I'll have 7,577 chlorine 35 for every 10,000 chlorine atoms. So if I feed 10,000 chlorine atoms into the mass spectrometer, 7,577 will strike here. And the remainder, there's only 2 isotopes, which I don't tell you there. The other isotope of chlorine is chlorine 37. The remainder will strike here. And so that will be about 25, a little less than 25%. It'll be 2,423 atoms strike there. Does that answer the question? Okay. Others? 31. All right, this is the same thing. Are these mass percentages or number / mole percentages? Whenever we have a percent natural abundance, is that by mass or is that by mole? It's by mole. It's by amount. Well, in this case, you don't need to know that. What we do is this. We want to figure out the abundance of H2O16H2. And so we know that H2 is 0.015%. O16 is 99.76%. And H2 again is 0.015%. And so how can I deal with these 3 percentages? Does anybody recall? I could try multiplying. If I tried multiplying these 3 percentages to get the percentage of the whole molecule, does that work? If I multiply it, I get percentage times percentage is percentage squared times percentage is percentage cubed. Is there such thing as a cubic percentage? No. So I have to use some fancy dimensional analysis for this. Does anybody recall? How did he do?
You have to convert to the percentages into fractions.
Yeah. So what we'll do is here, 0.015 out of 100 will be H2. And then this one will be 99.76. 99.76 out of 100 will be O16. And then this one we could leave as a percentage, 0.015%. And so now this is going to give us the units, the correct units, which would be percentage. It doesn't matter which two you convert. We have to just convert 2 out of the 3. And so if we convert 2 out of the 3, what we're going to get is 0.015. 0.015 times 99.76 times 0.015 divided by 100. Oops. Divided by 100. And I get 5 zeros. Five zeros, 224. And so that gives us D. D is the correct answer to that. This is the way I read this. A percent is parts per hundred. So this is 0.000005022 out of 100. I'm only allowed 2 6/8. Since I can't have a fraction of an atom, what I do is I just move this over, or a fraction of a molecule. Oh, this is a brand new pen. It's a blue one. One, two, three, 4, 5, 6, 7. We'll do the same thing here. 1, 2, 3, 4, 5, 6, 7. Then add the zeros. 1, 2, 3, 4, 5, 6, 7. And then figure out what that is. 1,000, million, billion. So this is 22 H2 O16 H2 out of 1 billion H2Os. And so if I have a billion water molecules, then I could expect 22 of those to be H2O16 H2 molecules. This would not be grams. Okay. Is that okay? Is that it? Are there other questions? Uh-huh.
It's on the chapter 4 homework.
Okay.
It's 11. It's one of the two variables, but I don't need the whole problem. I just need the first part. It's like about iron aluminum alloy, and I checked what it would be, the mass of the H2 would be if it's 100% aluminum and 100% iron, but I couldn't. My iron one seems low, and it's like not within the range.
Not within the range. Okay, let's see what that. Chapter 5?
Chapter 4.
Chapter 4.
What defines a molecule in a formula unit?
Same thing.
So,
Molecule and formula unit's the same thing, but we can't use one of those for NaCl. So we must use formula unit for this because NaCl does not form molecules.
got it.
What number was that?
111.
Iron and aluminum alloy. One of the mistakes that people make on these kind of problems is they assume that the iron and the aluminum are going to be in some ratio. So some people will consider ferroaluminum as 1 part iron, 1 part aluminum by mole. But when we have a mixture, is it going to be at a fixed ratio? No. In a mixture, we can have any ratio of iron and aluminum. And so what I see a lot of people do in this particular problem here is they'll do this. They'll try to combine the two. And so what they'll do is they'll call ferroaluminum 1 part iron, 1 part aluminum, like this. And then they'll add, the HCl just to figure it out. But we don't do that. They're going to react separately, and they can be in any ratio, not a 1-to-1 ratio. And so this is fixing the ratio 1-to-1. It doesn't have a fixed ratio. It's a mixture. Mixtures can have any ratio it wants. And so the critical thing is we have to do this separately. And so we assume it's all iron. This is how it reacts. Or we assume it's all aluminum. This is how it reacts. So you calculated the iron and it came out too low?
Yeah.
Which one gives us more hydrogen per gram of metal? And so when I look at iron, iron's about what, 63, is it? No, 55? 55.87. So iron's about 56. So if we have 56 grams of iron, it produces how much hydrogen? 2 grams of hydrogen, because mole of H2 is about 2 grams. And then this is 2 moles of aluminum. 2 moles of aluminum, well, aluminum is 27, so 2 moles would be 54. So this is 55, this is 54 grams of metal. 54 grams of aluminum produces 6 grams of hydrogen. And so the aluminum produces a lot more hydrogen per gram than iron, right? So aluminum should be at the higher. If this were pure aluminum, it's going to yield more hydrogen than if this were pure iron. Is that correct? Okay, so you're saying the lower bound is too high.
Well, now that you say that, actually, they're both too low.
They're both too low.
So one should be above 0.105 and one should be below.
Yes, we got to have one above 0.105 or equal to it, and one below.
Was 0.102, which is under.
Okay,
But I still thought that was okay. And then
that's okay.
my iron, I got 0.074.
Okay, that's not possible.
Yeah.
This falls outside the range. So one of the iron could be correct and the aluminum too low, or the aluminum could be correct and the iron too low. So let's just do a quick calculation to figure it out, which one it is. And since the iron's going to yield less, we'll start off with that. Let's say we're pure iron, 2.05 grams of pure iron. And then what did you use for the molar mass of iron?
55.845.
Okay, that's 55.847. We'll just go with 55.85. And then what did you do after that?
1-to-1 mole ratio.
Yeah. 1-to-1 mole ratio, 1 mole of hydrogen for 1 mole of iron. And then
And I did 1 mole of hydrogen is 2.01.
yeah, that's right. So let's see how many grams that comes out to. .05 divided by 55.85 times 2.016. You have 0.073?
Yeah.
this is going to be the lower bound. Now, if this were pure aluminum, that would be the upper bound. And so 2.05 grams of aluminum, a mole of aluminum, and we'll just use the smaller mass here, which is 26.98. And then what's the mole ratio here? Yeah, 3 moles of hydrogen, 2 moles of aluminum. And the same molar mass, 2.416 grams of hydrogen per mole of hydrogen.
Okay. That's where I messed up. I did 2 over 3, not 3 over 2.
Okay, that would do it. Yeah, we get 0.2297 grams of hydrogen. So it varies from 73 to 230. 73 to 230, and we got a 105. So it looks like it's closer to 73, which means more iron than aluminum. It should be greater than 50% iron. Okay, other questions?
Sometimes the book.
Experiment 5 pre-lab assignment calculation. Yeah, what was can you read the question? I don't have the pre-lab with
How
me.
many milliliters of oxygen gas are measured at 7.2 million Hg attracted and 23.8 Celsius by the displacement of water with respect to obtain from the decomposition of 1.500 grams of pure potassium chloride.
Okay, so let me see if I get the numbers correct. 757.2 millimeters Hg uncorrected. What was the temperature?
22.8 Celsius.
22.8 Celsius. 22.8 degrees C. And it was 1.50 grams of pure KClO3. 1.500 grams. What was the volume?
The milliliters, not asking to find out how many milliliters of oxygen gas.
Okay. So they want us to figure out the volume, calculate the volume of oxygen gas. Okay, that's right. Well, we're doing chapter 6. Actually, I was supposed to start it last time, so I'm out of sync right now.
Oh, I haven't started chapter 6 yet.
Yeah. In chapter 6, we use PV equals nRT. And so we want the volume. The volume of O2 is going to equal the moles of O2 times R times the temperature of O2 divided by the pressure of the O2. We want the volume of pure O2. This is the dry O2. And all these have to be dry as well. So in this case, we have to correct the barometric pressure here using the correction. We have to look it up on the table. Yeah. This particular calculation you don't have to do for the lab. It's not necessary. For the lab, we're doing a different calculation.
on the sheet, or would we do like a similar calculation to this?
No,
No?
no. It's going to be a different calculation. This calculation we could do, but I need to look at the table. And I don't have it, unfortunately. Here. So, ask me tomorrow in lab. I'll bring the table so I can put it on the screen so everybody can see it. How to do the mercury correction.
And so in the lab, when it asks us who the one or the gas tested, how would we do that?
The graduated cylinder. How many milliliters of water do you measure in the graduated cylinder?
What is the gas in this specific?
All that water, what's the origin of all that water? All that water came from oxygen pushing the water out. Because there's air in there. And so as you generate the oxygen combines with the air, makes the volume bigger. Well, there's no room, so what has to happen is as the oxygen's being generated, it's forcing the water out the tube into the beaker. So if you got, how many milliliters of water did you collect in the beaker? Then you got 258 milliliters of oxygen, because that's what caused the water to be pushed out. If you made 258 milliliters of oxygen, then you have to push out 258 milliliters of water to make room for that oxygen. Otherwise, the flask has no room. You only had, the flask had air in it and then water. The water was filled up to here. And so if you start adding more gas, you have to force the water out of the flask. The water gets forced out of the flask, so it gets forced out the bottom and then goes up that long tube. And from the long tube, it goes out into the beaker. And so the air is pushing down on the top, and now you're generating the oxygen. The more oxygen you generate, the more room it has to make, and it forces the water out. And so for every milliliter of water you get, you must have formed 1 milliliter of oxygen.
So the value you got for the volume?
The volume of oxygen is going to be 258 milliliters because you got 258 milliliters of water. Does that make sense? There's no calculation. The volume is measured. This is a different thing. This has no relation to any of the calculation we're doing. It's an interesting calculation. We should do it. But it's not related to any calculation you're doing for the report. Mm-hmm. Okay. But I can do the calculation tomorrow. I just got to show you the table. We have to do 2 corrections here. We have to do the correction for the barometer. Why do we have to do the correction for the barometer? Because normally, as things get hot, they tend to expand. Like a hot air balloon, it expands. Water, in general, as the temperature of water increases, the volume expands a little bit and the density goes down. It's kind of funny because it's parabolic. And so it goes more dense to 4. But once you hit 4, the higher the temperature, the greater the volume. The greater the volume, the less dense it is. And so the density goes down. Metals expand with temperature, expand and contract with temperature. So if you have a hot piece of metal, do you know it's a little bit bigger than a cold piece of metal? A little bit. And so, or it could be a lot. I was watching a documentary about the Concorde supersonic jet. Are you familiar with the Concorde? Mm-hmm. They're talking about how much the metal expands in the Concorde. It's ridiculous. It expands a huge amount. And then you think, wow, that's pretty scary. So the engineering must be good. Otherwise, that thing would fall apart, with that much expansion of the metal. You would think it would, But they had to do some, all kinds of structural studies for this to make sure the thing didn't fall apart. Because if you have metal expanding, is there room for it to expand? For us, there's room for it to expand because we just force the water out. The same thing with the barometer. The barometer has this, actually, we'll talk about the barometer today. Do you guys know how the barometer works? Pretty much? Do you remember from Chem 4 how the barometer works? We'll talk about why we need to correct it. Or do you remember what the barometer measures? What does the barometer measure? Pressure. Gas pressure. Gas pressure is the first topic in chapter 6. So let's take a look at gas pressure first. Gas pressure, if you have a gas, what does a gas consist of? A gas consists of a whole bunch of particles in chaotic motion, they say. It's in chaotic motion and it's moving around chaotically. And what's going to happen is there can be collisions. So the gas particle can collide with the wall of a container. And those collisions generate a force. And so pressure is the force of the collisions per unit area. And so if we had a square meter, we measure the force of those collisions. And do you know in physics what unit they give to force? Pascals is the unit of pressure. But force, the units of force are in newtons, named after Isaac Newton. And area is usually in meters squared. So Newton per meter squared is defined as a new unit. You know what unit that's called? It's called a Pascal. Pascal. Newton per meter squared. Here's the Newton. That's the SI unit of force. And here's the Pascal. 1 Pascal is the force in 1 Newton per meter squared, force over area. Pascals aren't that common. Well, actually, I had a bike tire. My bike tire had some weird, normally I'm used to inflating the bike tire to a certain number of PSI, but this bike tire had Pascals. I had to fill it to I think it was between 200 and 300 kilopascals pressure. But none of the bike pumps read kilopascals. Pascal is kind of small. This is in honor of Blaise Pascal. Do we use Pascals much? No. This is why my bike pump doesn't read kilopascals. When we think about force, one way of visualizing this is like a weight, The more force you have, the more weight there is on this surface. And so, one of the things we do is this. Normal atmospheric pressure or normal pressure This would be like room pressure. You know, there's room temperature, there's room pressure. So normal pressure, we'll just call room pressure. What is the normal room pressure in this room? What do you say? You know what normal atmospheric pressure is? 1 ATM.
760 torr.
Yeah, so normal pressure is 1 ATM, which is equal to 760 torr. Exactly.
And then you have the millimeters of mercury.
Yeah, which is 760 millimeters of mercury. Not so exact, but close enough to exact. We'll talk about why it might not be so exact here in a little bit. Which is equal to 14.7 psi. 14.7 psi is equal to 14.7 pounds of force. Pounds of force per square inch. Not in terms of meters. If we had square meters, it'd be more. But 14.7 pounds of force per square inch. Pounds would be another unit of force or weight. And so another way of visualizing this is like this. Normal pressure would be at sea level. And what we have is we have this. We'd have a blanket of air on us. And how much does this blanket of air weigh? This blanket of air weighs, 14.7 pounds per square inch. That's how much it weighs. That's at sea level. If we're on top of a mountain, are we going to have as much air on us? Let's say we're at the top of, what's the tallest mountain in California? Do you know what it is?
Shasta?
Shasta's pretty tall, but not the tallest. This is a little trivia question. Anybody? It's not in Yosemite. It's in Sequoia National Park. Whitney, Mount Whitney. Mount Whitney has 3 peaks. It's like the main peak is Mount Whitney on the right, and then we have Keeler Needle, and then we have Day Needle. So it looks like that. You can see Mount Whitney from the road, Highway 395. You can see it, but it doesn't look like the tallest because of foreshortening. Let's see, if you don't know what Mount Whitney looks like, let's show you here. That's what it looks like. So here's the main peak. This Keeler Needle, this Day Needle. Trail goes back around this way. It's 14,505 feet elevation. If you're standing at the top of Mount Whitney, are you going to have as much air blanketing you? No. So if you're up here, the blanket of air is going to be much thinner. You know, because actually the blanket of air, does it stay the same density? No. Actually, air gets thinner and thinner. Have you noticed that? As you go higher and higher in elevation. And so at the top of Mount Whitney, you're going to have a lot less than 14.7 pounds of air blanketing you. And so this is at sea level. We don't feel it. I mean, that's almost 15 pounds per square inch. 15 pounds is a lot of weight. But you don't really feel it.
If you're working out up there, then
Oh, you'll feel it because the air is very thin up there. You're going to get a lot less oxygen in your lungs.
There's also, I'm sure this has something to do with elevation and everything, but in Denver, the baseball stadium, Colorado Rockies, they have a high rate of home runs.
Oh, because less air resistance? Yeah. Yeah, definitely. I believe that for sure. Because the air causes a lot of friction. And so if you take physics, you'll have to calculate the friction. So the friction up here for an airplane is going to be a lot lower than the friction up here. So airplanes go, what, 60,000 feet or something above sea level? You know, it's not going to be nearly as much friction there if they travel at a lower elevation. Do you know how thick the atmosphere is? How tall is the atmosphere? And so, how thick is the atmosphere? Does anybody know? 8,000 miles. And the Earth's sphere, and thickness is about 60 miles. Okay. So you have about 60 miles. Is that right? 60 miles of air blanketing you. At the top of Mount Whitney, you'd have a lot less. Right? Not a lot less, a little less. And so that's it. And so this is equivalent to 60 miles of air blanketing you. Well, you know, the SI unit of pressure is the Pascal, but there are different ways to express the pressure. One way of expressing the pressure is as a height. You know, height of air. If you have 60 miles worth of air, then it's going to weigh 14, almost 15 pounds. But let's say you're 30 miles up, then you're only going to have 30 miles of air. 30 miles of air, would it be half the pressure? What do you think? If you're at 30 miles in elevation, are you going to have half the pressure? You would think so, but it isn't half the pressure. Why? It's a lot less than half. Do you know why? It's not linear. It's not linear. If the density were the same, then the density would be how many air particles in a volume. If the density were the same all the way up, then it would be linear. And that is, at 30 miles here, then it would be half because you have half as much, right? But the density kind of decreases, it's nonlinear. And so when something's changing, you know, like the density is changing here, so it makes the math more difficult because the density continually gets smaller and smaller. And so really to properly handle this, we need to use, not algebra. Do you know what we need to use for this kind of calculation? Kind of a graph, but it would be a nonlinear graph. But you know, what describes that kind of nonlinear, this thing that changes with altitude? The density is going to change with altitude. And it also changes with temperature. There are multi-factors in this. And so we'd probably have to use a more advanced form of this kind of math. What kind of math is it? Calculus. We have to use calculus. If we use some calculus, then we can figure out, because the density is going to change with elevation, the density is going to change with temperature. And so we can use calculus for that. But is calculus required for this class? No. And so what we could also do is we could just do some measurements. We could just measurement and take the measurements and then make a graph. And then from the graph, we can model that with a mathematical equation, an empirical equation. But that empirical equation is not going to be a y equals mx plus b type equation. It's going to look funny. In fact, somebody did that. So you could do this you could do this assuming the temperature doesn't change as we go up in elevation. They'll make it simpler, you know? And just the density changes. It's probably the easiest thing to do.
So I have here atmospheric pressure and density at Coors Field are on average about 20% less than a park at sea level.
Yes. Yeah. But, you know, I want to see the math of that. Because what if let's say we're at 8,000. I was talking to somebody at lunchtime, and they said they were from Bogota, Colombia.
And they told me Bogota Colombia is at 8,000 feet elevation. I didn't realize it was that high in elevation, 8,000 feet. You know, I actually climbed the top of Mount Whitney, but I ended up getting altitude sickness. I had a huge headache. And,
I was feeling nauseous. What's that?
Cocoa leaves.
Oh, cocoa leaves?
Yeah.
Grab them on the way there, but probably in Bogota, they have no problem with cocoa leaf. But when I came back down, then the headache went away. And I was feeling all right, but I felt out there.
But anyway, you could either use calculus, do it theoretically, or you can make a graph and make some experimental measurements, and then you can come up with an equation. And the equation has a name. Take a look at it. What chapter am I in here? Called the barometric formula. So this is problem number 117 from the homework. We have noted that atmospheric pressure depends on altitude. Atmospheric pressure is a function of altitude can be calculated with an equation